Ladies and gentlemen, welcome to machine learning. In this video, we will be talking about the Bayesian Supervised Learning approach. In the last videos, we talked about the probability theory and derived the bias rule. And in other videos, we talked about the regression problem. And in this video, we will be combining both of those methods. So let's jump right in. Which problems did we have with the frequentist approach? Well, first of all, we had data splitting. So the first part was used for training and the other part was used for validation. And we were using a significant chunk of our training data to evaluate our model. The other problem is that we have no access to uncertainty. So if our model returns us a number, for example, 3, we are not sure, or we don't know at all if the model is very certain in that result or that it is very uncertain in this result. The other thing is that if we use the normal regression problem that we had before, so for example, method of linear least squares, we can't add prior knowledge to our model. So we can say, hey, this parameter is probably positive and this weight or the bias is negative. And the last problem is, problem number 4, is that the approach without, so the frequentist approach without probability is very overconfident. For example, if you throw a coin and you get 2 times head, the frequentist approach will predict all future tosses to also be heads. But we can say, hey, this coin is probably on a 50-50 chance. So even if we threw the head 2 times, it's not very certain that we will continue getting head all the time. So the frequentist statistics, in frequentist statistics, we review probabilities as frequencies of random events, random repeatable events. And if we employ the Bayesian perspective, we see probabilities as measures of uncertainty. So what we are doing is uncertainty quantification. So we're trying to understand how certain are we in our results. So again, the bias rule, we got it from the sum rule and the product rule. Here we have 2 terms. And if we now divide by one part, we will get our bias rule. So we have probability of x given y times probability of y divided by the probability of x. If we are in a discrete case, we can use the sum rule, this right here, to get the probability of x. So we sum over all probability of x given y times y for all y. So I goes from, for example, 1 to, if we have 10 cases, it goes up to 10. So this is our bias rule. So now we come to the Bayesian Supervised Learning approach. We again have this, our bias rule, but in this case, we have as x is equal to theta, our parameters. So for example, our w's, then our y's are equal to our data. And then we add another dependency to each term. So we add it here, we add it here, and we add it here. And this will be, for example, the z will be our model. So now we have the probability of our parameters given data and model. And our bias rule will be then the probability of our parameters is equal to the probability of data given theta and model times the probability of theta given model divided by the probability of data given model. So this is our Bayesian parameter inference. We do not estimate parameters, but we infer them. So this expression is now our posteriori. And we get it by multiplying the likelihood, so the likelihood of our data, times our prior knowledge that we have of the parameters. For example, we can say that if we employ one specific model, we know that all the parameters, or we expect all the parameters to be positive. So we can say that this must be greater or equal than 0. So this is our prior knowledge that we can add to our posteriori prediction. And this times that is not yet a probability distribution. And to get it to a probability distribution, we have to divide by the evidence, and the evidence is that term. So our posteriori will be also a probability distribution. So we will get not a fixed value for our parameters, but we will get a probability distributions. And we will say for this value, we are the most confident, and for the other values, we are not confident. So again, the Bayesian supervised learning for the prior is a probability distribution, which encodes our belief about the possible values of theta that we know before observing any data. So before observing any data, we say that this model has probably positive parameters. The likelihood is the same likelihood that we had in the last videos. We say how probable our data is for a given set of parameters theta. Then we have the evidence, and the evidence is just our normalizing constant. And the evidence in this case is the integral of the probability of theta given theta in model times the probability of theta given model integrated over our theta. So here again, we have the posteriori, the likelihood, the prior, and the evidence. What is the difference between this approach? Let me get rid of that. What is the difference between this approach that we are now trying to employ and the frequentist approach that we had in the last videos? Well, in the frequentist approach, our results that we got were fixed. So we had fixed parameters and they were constants. So the value of these constants were unknown. So what we are doing is parameter estimation. In the Bayesian approach, our parameters are treated as a random variable, so we can express uncertainty in those parameters. So we obtain the probability distribution at the end. This is our posteriori, this one right here. We will get a probability distribution for those parameters conditioned on the data. So they depend on the data right here and on the model. And we call this process inference. So from the data, we will get those parameters. We infer them. We don't estimate them so that our likelihood, our data is most probable, but from the data, we get our parameters. So after we got our distribution, our posteriori distribution right here, we can use that to predict new outputs for new inputs. And we do this by the process of posteriori robust prediction. So once we have obtained our posteriori distribution function, we can use it to predict novel inputs. So the probability of a new input given data and model is a integral over this is our posteriori, and this is the probability of y given x, the input, of our parameters and model. So we have the uncertainty from the parameters here, of the output and propagated to the model or to the uncertainty of our prediction. So by doing that, we can say that because we're uncertain in our parameters, we can also say that we are uncertain or have a probability distribution in our output. So this is the biggest difference between the frequentist approach and the Bayesian approach. We're saying that because we're not sure in our parameters, they have a distribution, our output will also have a distribution. Let's summarize. So we had differences with the frequentist approach with data splitting, no access to uncertainty, no prior knowledge, and overconfident. And we solved those problems by applying our bias rule, but in this case, we added a model, so a dependency on the model. So that's why we have model here, and model there. And now we try to get the posteriori distribution, and with the help of the posteriori distribution, we can make posterior robust predictions. So we have our predictions and our posteriori distribution functions, and we will get a probability distribution of our outputs y. So we will see that how probable we are or how sure we are in our output. And we can say that, well, here we are unsure, and in that case, we are very, very sure that this will be the correct output. I hope this video gave you a small introduction into the topic of Bayesian supervised learning. In the next video, we will be talking about how we can actually calculate the posterior distribution function. Thank you very much for your attention, and I'll see you in the next video.